This is Chemistry 108, Chemical Principles 1 at York College, March 24th, and we're continuing in Chapter 5. So last time we talked about gases and we talked about pressure, and we looked at the YouTube manometer, right, and we thought about the outside of the atmosphere and the bulb and pressure. And we saw that we saw the definition of pressure. And pressure can be measured in different units. Right? This was a slide that we looked at, but we didn't see everything that we're going to see now. Right? Atmospheres is one of them, is one unit that we can use to measure pressure. What's another one that we learned? Millimeters of mercury, yeah. Torr, T-O-R-R, named after the Italian chemist Torricelli, is identical, for all intents and purposes, to the millimeter of mercury. And it's kind of nice because if you say millimeter of mercury over and over, it gets kind of long, but if you say torr, it's nice and easy. So, pascals. Pascals is the SI, or the metric, standard metric unit of pressure, or kilopascals. Kilo, in this case, is the same kilo as kilograms and kilometers, 10 to the third, or 1,000. PSI, pounds per square inch. This is typically what your tire pressure, for example, in your car is going to be measured in. Do you have to memorize these? You need to know, I mean, if you do these problems, you'll learn many of these just from doing them. But technically speaking, you don't have to memorize them except for the pascals to kilopascals. I mean, it's just like inches to centimeters. If they're not in the metric system, I'm not going to expect you to memorize them. But by the end of the semester, if you're like, or the end of the chapter, if you're like alive and breathing, at least this one you'll have down, right? A lot of the other ones you probably will have some impression of also. Okay, so pressure is one of the properties of gases. There's a lot of other properties that a sample of gas might have. Are there some that you can think of? So, some properties of gases. Let's say I have, I go to the party store and there's a tank full of helium, right, to blow up the balloons. Okay, so it's not organized. That's true. We haven't really talked about entropy, but this is not incorrect. Yep.
It's far apart.
Right, they're far apart. So I'm thinking about things like things that you can measure. Like pressure is something you can measure. Yes. Temperature, very good. Density, right. Volume, right. These are things that we can measure about a gas, or gas in a cylinder, or gas in a balloon, or something like that. Some of you did the lab already, and so you know all about that stuff. So in this class, we're going to consider very carefully, and eventually we'll get to density. Oh, oops, just kidding. So what happened to my slide? Okay, so let's see. Okay, so chemicals use the ideal or perfect gas as a model that approximates the behavior of real gases. And the reason, and so we talk about the ideal gas. Ideal gas doesn't exist, right? It's kind of a model. And the behavior of real actual gases like oxygen or nitrogen or helium, they behave almost exactly the same as ideal gases. And very often we can use the same. And we use ideal gases because there's a series of equations that makes a lot of intuitive sense, actually, that describes them, right? So they don't exist. We pretend they do. And when we do that, we'll consider the following properties of gases, or of the ideal gas. And you talked about some of them. We'll talk about pressure, we'll talk about volume, temperature, and here's another one. How much gas do you have in terms of, from the molecular point of view, right? The number of molecules or the number of moles. And there's our favorite unit, because as we'll continue to see in this section, once you know something about moles, you can find out lots of different things about, about your gas. So pressure, volume, temperature, number of particles or moles. These properties are related to one another in the ideal gas model, according to the following equation. P, which is pressure, times V, which is volume. So if you have a sample of gas in a container, the pressure of the gas times the volume of the gas equals the number of moles times R, which we'll talk about. R is a constant, times the temperature. So PV equals nRT. Right, that's going to be like your best friend for the next couple of weeks. Temperature is always in Kelvin, correct. And R is what we call the ideal gas constant, and it has a value. Right? And again, you don't have to commit this to memory, but if you're doing it right, you will have memorized it by the end of, a week or two, or week or so. R is equal to 0.0821 liters atmospheres divided by mole Kelvin, or 8.314. There's different ways to look at this. Liters times pascals times over mole Kelvin, or 62.314 liters times torr per mole Kelvin. And we'll talk about that, this very strange, funny unit over here. We'll talk about where that comes from very soon. And so what do you notice right away? Volume, when we're doing these calculations, will have to be in liters. Temperature is going to have to be in Kelvin. Moles is moles, number of moles. But P, pressure, can be, because there's atmospheres here and pascals here and torr here, you can use different units for your pressure. If you use torr for your pressure, then you have to use this variety of R. If you use atmospheres for your pressure, you need to use this variety of R. If you use pascals, you use this one, right? So that's why you have different values for the same constant. So let's do a simple calculation here. If I have 5 moles of an ideal gas in a 1 liter container at 200 Kelvin, and what's the pressure in pascals of that gas? How are we going to do that? Well, the equation says PV equals nRT. Do we know the pressure? No, that's what we're trying to find. Okay, do we know the volume? Yeah, we know the volume. It's 1 liter. Do we know the number of moles? It's 5 moles. Do we know R? Yeah, we do. And which variety of R are we going to use? 8.314, because it asks for pressure in pascals, and this is pascals, right? And then what's the temperature? 200. So we know everything except for P, right? We know V, we know N, we know R, we know T. So what we can do now is plug in, right? That's something we can do. So we don't know P. We don't know P. The volume is 1 liter equals N, which is 5 moles, right? times R. And what's R? R is 8.314. Liters times pascals over mole Kelvin. And what's T? T is 200 Kelvin. Let's do some unit canceling, yeah? So the moles are going to cancel with the moles, because this is on the top and this is on the bottom. Right? It's liters times pascals divided by mole Kelvin. And the Kelvin and the Kelvin are going to cancel. And so what we have now are liters times pascals. And so when we do the math out, oops, what are we going to get? We're going to get P, I'm just going to do this kind of slowly and stepwise, equals 5 times 200, which is 1,000, times 8.314. So that's going to be 8,300. We're kind of playing fast and loose with our significant figures. Let's assume that this, this, and this are all exact values. So we're going to have 8,314 liters times pascals. Right? So I did the multiplication, dot, dot, dot. The units that are left are liters times pascals. And so how do I want to solve this? I want to solve for P. If I divide both sides by 1 liter, right? And then this side by 1 liter, this all cancels. My liters and my liters cancel. And what do I have? P, you have pascals, equals 8,314 pascals. 5 times 200 times 8.314. Yeah. So I did the multiplication of all those numbers on top. Well, that's a matter of taste, and that's actually the next thing I'm going to show you. You can do this, or if you know what you're solving for, you know you're solving for P, what you can do is rearrange this thing, right? I can divide both sides by V, and then my V and my V cancel here, and what am I left with? I'm left with P equals nRT over V, and then I can plug right into this. Eventually you'll wind up doing the same calculations. Many times, almost all the time, what you'll have is you have these 5 letters, essentially, right? These 5 quantities: pressure, volume, moles, the gas constant, and the temperature. The gas constant is constant, so you know what that is, or you can look it up. So you have P, V, and T. Out of those 4, you'll know or be able to find 3 of them, and you'll have to solve for the 4th. So let's say the question is not this question, but it asked you for the temperature of the gas. If it asked you for the temperature of the gas, and you wanted to manipulate the equation first, what would you do? You would have PV equals nRT, and how would you get T by itself? Divide both sides by nR. And you would get T equals PV over nR. So either way works. If you like to do it like this and just do the algebra with numbers, that works. If you like to do it like this and do the algebra first with the letters and then plug in and just do arithmetic, that's fine too. Oh, before we do that, let's look at R. Let's solve this for R. So R is going to be PV over NT. Any questions here? Sorry? That's the constant. Right. And so what I'm trying to do now is why am I solving for r? I'm solving for r because I want to show you how we got the units to r. Right. And so the units to r, let's pull this down. Are something like that, right? Liters, atmospheres divided by mole Kelvin or something. And so what's pressure? Well, pressure is our unit of pressure. Let's say it's atmospheres, okay? So pressure is in atmospheres, or it could be in pascals or torr. Volume, what's that in? Liters. And so that's what's on top. What's on the bottom? N, which is in moles, and T, which is in Kelvin. So what do we have? We have liters atmospheres, or you can multiply in either order, right? So liters times atmospheres divided by mole Kelvin. Or if we wanted to do something besides atmospheres, we could do liters times pascals over mole Kelvin, or liters times torr over mole Kelvin. When you have liters times pascals, well, we'll talk about that later. Let's leave that here for now. Okay, so a short note on math, right? Because PV equals nRT is what's called the ideal gas law, or the complete gas, something like the complete gas law. Your book does this, if you're following along with your book, in kind of a different order. Right? There's different relationships. And your book kind of presents these binary relationships first. Right? And so there's, out of the ideal gas law, you can get different kind of smaller gas laws. And so there's one law that says, well, we'll talk about that. But that talks about pressure, the relationship between pressure and volume. There's another law that talks about the relationship between pressure and temperature. And these laws are laws that you can, that kind of make some sense if you think about them a little bit. And so let's talk about this one first, right? Let's say we have a container like this, right, with a piston that we can either push down or pull up, right? And so when I push down the piston, what do I do to the volume of the container? Right, if I push it down from here to here, the volume went from this to this, right? The volume decreased. There's no more room here, right? But if I keep pulling it up and the walls were higher, the volume would increase. Now, as I push it down, the volume decreases, right? When the volume decreases, what do you think happens to the pressure? It increases, right? And that kind of makes sense because you're exerting a force, right? And what's the pressure is force times area, right? It's related to force. Okay, so let's say instead of that, I had a stainless steel box, right? So it's not going to break or anything like that. And I have my gas, and I heat it up. What's going to happen to the pressure? Is it going to get, the pressure going to get higher or lower? It's going to get higher, right? What happens as I heat this up? The gas molecule is going to move faster. When the gas molecules move faster, they're going to bang into the wall harder. They bang into the wall harder. There's more force. There's more pressure, right? On the other hand, if I have a container like this, right, and I have my gas, it's a different kind of container. Right? It's not rigid. It has this movable thing, movable piston. If I heat up the gas, what's going to happen here? The thing's going to go up. Right? That's kind of what happens in your car. Right? These things go up and down. And so when it goes up, what happens to the volume? Increases. So there's a relationship between, volume and, in this case, pressure and temperature. Pressure and volume is right there, right? Pressure, nope, wrong. Volume and temperature. Now, what about if I have this situation and I have a little needle here and I add more gas into this container? What's going to happen to the pressure? It's going to increase, right? And these things, because there's more gas molecules. More gas molecules are going to be hitting the wall more. It's going to have more force. Right? And so this equation describes all those things, all of these relationships, plus some more. We'll kind of formally introduce them. In some cases, one increases, the other decreases. In some cases, one increases, the other increases. Sometimes they go up together, sometimes they go up in opposite. And that's exactly what the note on mathematics is, right? So let's try to, let's do this. Okay, if I have two variables, A and B, right? And they have this relationship, A equals K times B. Or we could even call it A equals R times B, where R is a constant. It could be the gas constant, it could be some other constant. Then, if A is 1, or as A goes from 1 to 10, that is, A increases, what happens to B? It also increases, right? So let's say R equals 8.31. If R equals 8.31, if A is 1, then B is 8.31. If A is 2, B is 16.62. If A is 3, B is 24.93, and so on, right? As one gets bigger, the other one also gets bigger. And this number is called the proportionality constant. Right? That means they're proportional. They get bigger together.
Can R and B be interchangeable? Can it be for
Well, if we say R is a constant, right, then it's going to be R is going to define the relationship between A and B.
But then B can also be a constant if you make it in that problem, so it doesn't matter.
Right. If B is constant, then R would change. Right. But I'm just using R because R is the gas constant, and so we're kind of thinking that that's constant. So if I rearrange A equals R times B, and I say, and I solve for R, what am I going to do? I divide both sides by B. I get R equals A over B. This is really the same thing. These are really saying the same thing, right, because they're the same equation. That means as one goes up, that's also saying this. That means as one goes up, the other goes up. And the way we term that is they are directly proportional. Directly proportional means as one goes up, the other goes up. And so, if we have the opposite relationship here, okay, let's erase all of this. No, let's not erase that. It's directly proportional. R equals A divided by B. If we have now A equals R divided by B, what happens when A gets bigger? let's just say for now R equals 1, right? Because that's easy. If A is 1, then B equals 1. If A is 2, B is 1 divided by what gives you 2? 1 divided by 0.5 gives you 2. If A is 3, what's B? B is 1/3, right? 0.333, or 1/3. If A is 4, B is 0.25. As A gets bigger, B gets smaller. Right? So another way of writing this is, if I multiply both sides by B, is R equals A times B, and that's indirectly proportional. As one gets bigger, the other gets smaller. Okay, so what do we care about that for? Okay, we did all of that, we did all of that. Okay, yeah. Okay. Now, okay, so here's the ideal gas law. Now, if we can set up conditions where the temperature doesn't change, that's not too hard, right? Because if you have, a thermostated reaction chamber or something, have really good air conditioning, then you can do a reaction or do something where the temperature is held constant. And the number of moles doesn't change. That means you have a closed container. No gas gets in, no gas gets out. So if the temperature doesn't change and the number of moles doesn't change, what does that mean in this equation? That means N is constant and T is constant. And R is always constant, right, because R is a constant. So what does that mean? That means PV equals a constant. Whoops. Whoa. That's supposed to be gray. Okay. Okay, so if N doesn't change and that's an and T doesn't change, then we get PV equals nRT, where these are all constants, right? These don't change at all. So we get if we call this K, we can say PV equals K, right? We just kind of replace the nRT with a single letter K. If we have PV equals K, then we can also get something like this, right? P equals K over V. And there's two ways to look at this. They're kind of equivalent. They're of course mathematically equivalent. What kind of proportionality is here? Direct or indirect? Indirect, that's right. So what does that mean? That means as the pressure gets higher, volume gets smaller. Right? As the volume gets bigger, the pressure gets smaller. Right? These, as one goes up, the other goes down. As the other goes up, the first one goes down. You can think about it mathematically either way, but that means these are indirectly proportional. As one goes up, the other goes down. As one goes down, the other goes up. So can someone tell me what this means in English?
Pressure times volume.
That technically is English, but not math. But in chemistry, or in English, or in gas.
As like P goes up, V goes down.
As P goes up, V goes down. We're moving in the right direction. How about something like this? The greater the pressure, the less, or the greater the pressure, the smaller the volume. Something like that, right? And the greater the volume, the lower the pressure. As pressure increases, volume decreases. So what does this mean? That means if the temperature doesn't change, the number of moles doesn't change, then the only things that can change are P and V, right? And so what's your situation? What's your situation like that? Your situation is like this, right? And the only if you change the pressure, if you change the pressure, the volume goes down. Or if you increase the pressure, the volume goes down. If you decrease the pressure, the volume goes up. And so this is kind of intuitive, right? You told me before we started looking at letters exactly that, right? If you increase the pressure, the volume goes down. That's what it means. Okay, yeah. These slides are all messed up. Okay.
We also said that if you increase the temperature, that would make the pressure higher, and then that would make...
Right, but in this case, let's take a step back. Okay, these, I don't like, I'm going to turn these slides off soon. But we set up conditions where the temperature doesn't change, right? And the number of moles doesn't change, right? So in that case, these are the only two things that change. If you could increase the temperature, then that could also affect either the pressure or the volume, right? Oh, I should have left that. That's okay. So let's say we go from this case, right, to this case. Right, so we went from here to there, and this is state 1, and this is state 2. One of the benefits of writing it this way is that you can see that K doesn't change. Or in other words, P times V doesn't change. So in state 1, you have a certain pressure and volume, P1 and V1. And in state 2, you have a new pressure that's higher and a new volume that's smaller. Right? And so you have P2 and V2. In both cases, P times V equals a constant. So how can we put them together? They both equal K, and it's the same K. So P1, V1 equals K. P2 times V2 equals K. They both equal K, so they must equal each other. So we get P1 times V1 equals P2 times V2. Right? And that statement, or that simplification of the ideal gas law, when temperature and moles don't change, gets known as Boyle's law. Now, I don't particularly care for names, but some people do, because it's all really coming from the same place, but some people do. And so, you know, maybe Mr. Boyle likes his name on his law. And so we get the quantitative relationship between pressure and volume. Okay, yeah. Okay, so now instead, if we want to instead set up conditions where let's say if we set up conditions where the pressure doesn't change, the pressure and number of moles of gas, or the amount of gas, don't change, then let's kind of do the same thing. We get PV equals nRT, right? And then R is constant. In this case, what else is constant? P and N. So if we solve, let's divide both sides by PT. On this side, T cancels. On this side, P cancels. We get V over T equals N times R over P. Why did I do that? I did that so all of the unchanging letters, all the unchanging quantities wind up on one side, right? Because R is a constant, and I'm setting up conditions where P doesn't change, right? Pressure doesn't change, and N doesn't change. So V over T equals a constant. We can call it K if we want again. V over T equals K. What kind of proportionality is that? Indirect or direct? Direct. As one goes up, the other one also goes up at the same time. The other way we can write it if we want is V equals TK. Right. As V goes up, then T goes up, and K is called the proportionality constant. So, can somebody explain this to me in English? Yeah.
When the volume increases, the temperature increases also.
Yes, this is true. But that's a little bit of a strange way to say it, right? Because generally we're not going to be starting by increasing the volume or decreasing the volume. Usually we're going to change the temperature first, right? It's easier to change to think about that. So let's try that as the temperature changes or as the temperature increases, then what? Right. If the temperature of a gas increases, the volume increases. As the temperature of a gas decreases, the volume decreases. And so that's exactly what you mentioned with the piston, right? And so if we have the same thing, right, we have our, let's say our V1 and our T1, and then we raise the temperature, right? We raise the temperature, and then we get this. We have a V2 and a T2. What's the relationship? It's not P, it's not like that. It's going to be like this. V1 over T1 equals V2 over T2. Right, and that one, again, I don't like names. I think that's Charles' law. Yeah, that's Charles' law. Okay, and so questions here? Yeah.
So the reason why you brought PT over was to bring all the constants on one side?
Yeah, so I brought T over to this side, and I brought P over to this side. Yeah, and so now all the constants are on one side, and all the not constants, the ones that can change, are on this side. Right, and once we realize that these are all constants, they don't change. So I just gave them the whole thing its own name, K. Okay, so goodbye, Mr. Boyle. If we set up another set of conditions, and we won't do all the possible conditions. Once you look at 2 or 3, you can kind of get it. Right? So if we set up conditions where temperature and pressure don't change, So now temperature and pressure don't change. We want to get everything that doesn't change on one side, everything that can change on the other. So R is here. Let's leave R. Temperature is here. So pressure has to go on this side, and N has to go on this side. So if we divide both sides by Pn, the P's cancel here, the N's cancel here, and I get V over N equals RT over P. R doesn't change, T doesn't change, P doesn't change, so I can say V over N equals K. Can someone can someone tell me what that means in English? Mumble, mumble.
The higher the moles, the more volume.
Yes, the higher the moles, the more volume.
Higher the volume, the more.
That's not bad, right? So moles is really, the more moles you have is really, you have more gas, right? So as you add more gas, the volume gets bigger, right? What's an example of that? Balloon, right? You blow up the balloon, you add more gas, the balloon expands. Yeah. So there's a couple of ways to say this, right? If we wanted to do the exact same thing here, we could say this: V1 over N1 equals V2 over N2. Another way that this is often stated is V equals N times K. Right? And so these are two different ways of saying the same thing, and this is called Avogadro's law. Hey, look, there he is. And he's there because this one has to do with moles. Right? So we're going to, I'm going to plug this in because I'm going to bring the slides back just real quick. So here's your ideal gas law again, PV equals nRT. And from that, if you have constant N and P, you get Charles' law. V1 over T1 equals V2 over T2. If you have constant N and T, you get Boyle's law. P1 over V1 equals P2 over V2. If you have constant P and T, you get Avogadro's law. Yep, we can write it like that. Or you put them all together, you get the combined gas law, P1 over V1 over T1, P1 times V1 over T1, P2 times V2 over T2. What's the assumption here? Moles are the same, right? This is for the same amount of gas, same number of molecules or same number of moles of gas. P1 times V1 over T1 equals P2 times V2 over T2.
What about when moles and pressure and volume are the same?
Okay, say that again. Which two are the same?
Moles and volume.
Moles and volume are the same. That's actually what I was going to ask you next. So if moles and volume are the same, what changes? Temperature and pressure. And what's the relationship there? Let's write this out. See, I had one version that actually had this, and it's somewhere. So at constant moles and pressure, what changes? V and no, moles and temperature. No, moles and volume. At constant moles and volume, that's one of the things that's left, what changes? What changes are temperature and pressure, right? And so in English, what's the relationship between temperature and pressure? Temperature increases, pressure increases. So is it going to look like this, or is it going to look like this? Green or blue? It's going to look like green. It's going to be P1 over T1 equals P2 over T2. And this is what's called, I believe, again, I don't like names and I don't remember names very well, but I think this is called Gay-Lussac's law. Questions? Okay, so we'll take a break now, 10 minutes, and we'll do some problems when we get back. So standard temperature and pressure are conditions known as, are sort of defined conditions in gas chemistry. And these standard conditions, when we're talking about gases, are conditions of 1 atmosphere of pressure and 273 Kelvin temperature. And so let's use the ideal gas law to find out what's the volume of 1 mole of an ideal gas at STP, at standard temperature and pressure. So if we look at these conditions, what are our knowns, right? We have P, pressure, V, volume, N, moles, and T, temperature. Do we know P? Yep, 1 atmosphere, right? 1.000 atmospheres. Do we know V? No, that's what we're trying to find, right? Do we know N? 1 mole, exactly 1 mole. And do we know T? And do we know R? Yes, we know R, right? R is, which R are we going to use?
0.0821.
0.0821, because that's in liters times atmospheres over mole Kelvin. So what we can do is, if we want, we can rewrite our equation, right? Divide both sides by P, so V equals nRT over P. We're trying to solve for V, remember? And we plug in 1 for N, 0.0821 for R, 273 for K, and 1 for atmospheres. And so sometimes when we're doing these gas law problems for convenience, we won't write down all the units, but here we're going to write them out. So N is in this light green, right, or the cyan, or whatever this is, 1 mole times 0.0821 liters atmospheres over mole Kelvin, right? This kind of yellowish, bright yellow-green color is your whole thing is your R, right? 0.00821 liter atmosphere per mole Kelvin, right? So that's nRT, 273 Kelvin, divided by P, 1 atmosphere. And look what cancels. Moles and moles cancels. Atmospheres and atmospheres cancel. Kelvin and Kelvin cancel, and what's left is L. Okay. Right, moles and moles go. Kelvin and Kelvin go. Atmospheres and atmospheres go, and what we're left with is L. And when you do the math, if we consider exactly 1 mole, right, so we don't think about the significant figures of its exact number, the volume is 22.4 liters. And another way or the way to say this in English is the volume of 1 mole of ideal gas at STP is 22.4 liters. 1 mole of ideal gas at STP, or 1 mole of gas at has volume of 22.4 liters at STP. So these PV equals nRT problems, they're probably the most straightforward of the bunch, right? You have 3 of them, right? 3 of the 4 quantities variables. You have some information about them, and you find the fourth. Now, the next few questions have like headings on them, so you'll know what formula to use. When you're looking at them on an exam or something, that won't be the case, right? So these are just kind of examples. Right? You still need to go and do tons and tons of practice. If I use a piston, a container with a piston like the one on the left to compress a sample of gas. In sample A, the volume is 2.25 liters and the pressure is 100 kilopascals. In B, the volume is 1.35 liters. What is the pressure in B? Now, before we even do any math, is the pressure in B going to be greater than 100 kilopascals or less than 100 kilopascals? Greater, right? Because the volume got smaller, the pressure gets greater. So P1 times V1 equals P2 times V2. What's P1 here? 100. What's kilopascals? What's V1? And we're trying to find P2. What's V2? 1.35, right? So P1, V1 equals P2, V2. P1 is 100 kilopascals. V1, 2.25 liters. P2, we want to find out. V2, 1.35. And so what do? We divide both sides by 1.35 to get P2. The liters and the liters cancel. What's left? Kilopascals. And we get P2 equals 167 kilopascals. Questions here? Okay, so Charles' law, V1 over T1 equals V2 over T2. So if I heat up a balloon, and assuming it doesn't melt and it doesn't pop, then it's going to expand, right? So this is what you figured out already. So let's say I have a balloon filled with 0.500 liters of an ideal gas at 25 degrees Celsius. And now I heat it up to 40 degrees Celsius. What volume of gas does it now contain? So this relates volume and temperature. So volume and temperature is going to give you V1 T1 over V2 equals V2 over T2. So if you think about this before you try a problem, you think, what do I know? This question is asking me about volume and temperature. What do I know about the relationship between volume and temperature? If the temperature goes up, the volume also goes up. Okay, so that's a direct, one gets bigger, and if one gets bigger, the other one gets bigger, or directly proportional. In that case, it's always one over the other, right? So V1 over T1 equals V2 over T2. What's V1? 0.500 liters. What's T2? Very good. Somebody said something. 298. It's not 25. Why is it not 25? This temperature is always going to be in Kelvin. So temperature, first thing we need to do is convert the temperature. You convert from Celsius to Kelvin by adding 273. So T1 is 298. T2 is 313. And then we're going to do Charles' law. So V1 is 0.500. T1 is 298. V2 we're trying to find out. T2 is 313. I'm going to multiply both sides by 313. And I'm going to get 0.500 liters times 313 Kelvin equals 298. Right, if you want to cross multiply and do it that way, you can do it that way too. And when the math comes out, I get V2 equals 0.525 liters. Questions here? Okay. So we'll do a couple more examples, and yes, these slides are going to go onto Blackboard before the, tonight or tomorrow, or maybe the day after, but not too far from. Oh, that's not a good question. Okay. Okay. So what's going on here? So the question is this. if a balloon filled with 0.10 moles of air, we'll assume air behaves as an ideal gas, at STP contains 2.24 liters of air, then what's the volume of a balloon filled with 0.2 of the same sort of balloon filled with 0.20 moles of air? Well, the assumption here is that you're in the same place, right? And if you're in the same place, the atmospheric pressure is the same. Nope. Yep. Nope. Yep. Okay, the pressure is the same. And if you're in the same place, what else is the same? The temperature is the same. In this case, it's giving you STP, right? But the STP you actually don't need to use. The STP is just there to tell you that the temperature and the pressure don't change. So we have V equals K times N. And if we want, we can do it this way and find out what K is and plug in. But we can also do V1 over N1 equals V2 over N2. Right, so what's V1 here? V1 is 2.24 liters. N1 is 0.10 moles. And V2 is what we're trying to find out. And N2 is 0.20 moles. So how can I do this? I multiply both sides by 0.20 mole. The moles and the moles cancel, and I get V2 equals 4.48 liters. And actually, because these are two significant figures, I'm going to get equals 4.5 liters. Questions here? Not too bad, right? Wrong? Well, one way or the other, it's going to get a little more interesting very soon. What's that? Well, these are all straightforward, right? And the straightforward variety is okay, right? That's where we start. Now, okay, so yeah, we did all that. Okay, let's do this one now. I have 20 liters of CO2 gas at STP. Assume CO2 gas behaves like an ideal gas. How many grams of CO2 do I have? Okay, how do we do this? P is pressure, V is volume, N is moles, R is R, T is temperature. There's no mass, no grams. Yes, what do we need to do? Yep, go ahead. You find the moles first. If we find the moles first, what comes next? You know how to convert moles to grams. You use the molar mass. You just did that. So let's do it. Do we have some? Yes, we do. Okay. So I'm going to plug in. It's STP, so the pressure is 1.000 atm. The volume is given, right? It's 20 liters, 20.0 liters. R is R. It's given in, the pressure is in atm, so the R is in atm. And temperature is also given, STP, 273. And there should be a K there, right? That K somehow fell off. I think it's actually off, no, maybe, I don't know. There's a K there. We do the math. We solve for N. N equals 0.892 moles. Right? I mean, you can plug the numbers into your calculator to make sure that I didn't lie to you. Then we find the molar mass of carbon dioxide. We're going to assume we know how to do that. I abbreviated our molar masses here to one decimal place, 12.0 for C, 16.0 for O, so 44.0 grams per mole. We're maintaining the same number of significant figures here, right? 3 significant figures. And what do I do next? I multiply, whoa, that's all kind of funny, okay. The moles that we calculated times the molar mass, grams per mole. The moles and the moles cancel, and I get 39.2 grams. Questions? So this was kind of one step beyond just plugging into PV equals nRT. This requires, as many of you figured out, this requires you to be able to, once you get N, go from N to moles. And the calculation is not that hard. You know how to do the calculation. What might be a little harder is the realization that that's what you have to do. So let's do next the following. Can we find the molar concentration of the gas? Gas, just like solutions, can have a molar concentration, right? And what's the unit on molar concentration? Moles per liter. So the big M equals moles per liter. So what's the molar concentration of this gas? So we have moles, right? We got moles up here. And so 0.0892 moles. And do we have liters? 20.0 liters. And yes, sir. Say that again? 0.892, that's right. Okay, and I think I have the answer on another slide, but I want to keep all that information here, so I'm going to do the calculation, unless someone has it already. 0.892 divided by 20.0 equals 0.0446 moles per liter, or 0.0446 molar, capital M, big capital M. Can we do, what else can we find out? What's a quantity that one of you told us about way in the beginning of class, an hour and a half ago? Density. Can we find density? What's density? Mass over volume. Do we have mass? Yeah, 39.2. Do we have volume? Same volume. So unlike molar concentration, which is very specifically moles per liter, density doesn't have any particular units. It could be grams per liter, milligrams per liter, milligrams per milliliter. So we'll just leave it the way it is, grams per liter. So 39.2 grams divided by 20.0 liters, and that equals 1.96 grams per liter. Sorry? Questions? Okay, so there's one thing here that was very interesting, right? We used the molar mass. So that means somehow, right, maybe you don't know exactly how to do it, but by now it should be clear if you can use the molar mass and find other things. If you have other things, you should be able to calculate the molar mass. Okay, we talked about density. Yeah, we talked about density. Here's an equation. Molar mass equals the density times RT over P. Oh, sorry, just kidding. And that's kind of the end product. Now, there's a few ways to do this, right? So, and you can see that that's kind of sort of somehow related to the ideal gas law, PV equals nRT. How are the two exactly related? Well, let's think about that. Here's the equation, don't freak out. PV equals nRT, right? And we're getting here molar mass equals D times RT. Right, so molar mass is grams divided by moles. What's density? Is going to be grams, for example, right? So I'll leave it as grams divided by volume times RT over P. So RT over P, right? RT over P. What's density? Mass over volume. I left it as grams, right? So grams over volume. And what's molar mass? Grams divided by moles, or grams divided by N. So how can I get rid of this funny look, get rid of these G kind of things, right? Well, because there's no G here. Well, let's try this. Let's multiply, or let's divide both sides by G over V. Right, if I divide by G over V, it's the same as multiplying by V over G, right? So V over G, this cancels. V over G, those cancel, right? And what do I get? I get V over N equals RT over P. Can I get from here now to here? If I multiply both sides by NP, I get P over V times V equals N times RT. So indeed, this equation is the same as this equation. They just look different. Chemistry, yeah. So the molar mass equals a density times RT over P. We'll do a problem next time. The last thing I want to do is what's called Dalton's law of partial pressures, or get partial pressures. In order to get a partial pressure, or to talk about partial pressure, we're going to start with a quantity called a mole fraction. Right, so a mole fraction is often defined by this big Greek letter chi that looks kind of like a curly X, equals the moles of something, we'll call it X, in a mixture divided by the total moles of everything in that mixture, including X. Right? So if I have a mixture of, since we're talking about gases, if I have a mixture of oxygen and nitrogen, then the mole fraction of oxygen equals, so if I have a mixture of oxygen and nitrogen, then the mole fraction of the oxygen equals the moles of O2 divided by moles of O2 plus moles of N2. Right, that's the moles of oxygen divided by the total moles. Questions? Yeah, no. So one more thing here, right? If I have PV equals nRT, and the volume doesn't change, and the temperature doesn't change, what do I get? I get P1 over N1 equals P2 over N2. Right? And so this is going to be constant V and T. So as the temperature doesn't change and your vessel, your gas vessel doesn't expand, it's not a balloon, right? So a lot of times what you'll see is it'll say a rigid container or a rigid vessel at constant temperature. What does this mean? This means if the container doesn't get bigger as you add more gas, what happens? The pressure goes up. The pressure increases. That's why you get a tummy ache, right? Right. So, because P and N, another way of looking at it is P1 equals, or P equals K times N, right? P and N are directly related to each other. They're proportional. So it turns out that if we have a mixture of gases, right, if in our vessel we have O2 and N2, in that vessel there'll be a certain pressure, right? That pressure comes from both the oxygen and the nitrogen, because there's oxygen in the vessel and there's nitrogen in the vessel. And so the pressure in the vessel we're going to call the pressure total. But there's also partial pressures, right? So the pressure exerted by each individual component is going to be a partial pressure. And so the O2 is going to have its own partial pressure. And then the N2 is also going to have its own partial pressure. And it turns out, as you might expect, the total pressure equals the pressure of, in this case, O2 plus the pressure of N2. In general, it's going to be the P total equals the pressure of the first component plus the pressure of the second component plus, if there's more components, the sum of the pressure of all the components. Now, if you do some math, we're not going to show you all the math, is that you can get is that, right, this kind of makes sense. This is moles over moles. The mole fraction can also be described as, in this case, the partial pressure of O2 over the partial pressure of O2 plus the partial pressure of N2. And so this is essentially one way to state Dalton's law of partial pressures, right? The pressures, the partial pressure of each component of a gas equals or is proportional to the mole fraction, the moles of each component in a mixture. Right, so let's give you the exact wording here. The total pressure of a mixture of gases equals the sum of the mixtures of the individual gases and the pressures are proportional to the moles. Okay, and so I do want to give back your tests, so we'll stop right about here. Next time we'll do some more examples of gas laws, including density. We'll do some examples of this, and then we'll move on to some more theoretical considerations. Okay.